Hi. So we are going to be able to describe what happens. Well, basically, we're talking about springs, and the relationship between force and extension. It's all about some guy called Hooke and his law. But we'll start off by reviewing some important points. Can you put the following in order from the smallest to the largest? Kilo, milli, mega, micro, giga, and nano. Can you write down 4 equations that involve energy? And what are the units for the following measurements? Energy, power, force, and distance. Right, pause, answer, and then unpause once you've done. Okay, hopefully you've answered those questions. Let's just check what the correct answer is. So the smallest to the largest, the smallest is nano. Use the letter N. Then the next is micro. That is the Greek letter mu. Then we have milli with lowercase m. Then we jump a whole section and then we go to kilo, which is a lowercase k. And then mega, which is a capital M. And then giga, which is a capital G. 4 equations for energy. You can have work done, which is force times distance. You can have gravitational potential energy, GPE, which is mass times gravity times height. You can have kinetic energy, which is half mv squared, ke. And you can have electrical energy, which, let's do power. Energy related to power. Power times time is energy. All of those are energy equations. And what are the units for them? Energy is obviously in joules, power is in watts, force is in newtons, and distance is in meters. They're all capital, that one is lowercase. Okay, so before we were talking about forces, and when we have unbalanced forces, and what are the effect of unbalanced forces? If forces are unbalanced, if there is a net force on an object, the consequences are you either get something speeding up, so accelerating, changing its speed, so it can either accelerate or decelerate, speed up and slow down, or it could change its direction. If you're going one way, a new force can make it go a different direction. The third one is it can change its shape, and we didn't really look at that before. But here is an example of what happens when you have a net force on a material. You normally need more than one force. If you just have one force, something will just spin. So, for example, this one here, if just one of those forces, even if it would be a net force, the object would just move. Same with one of these. If you just have this, the object would probably just spin round. You need more than one force often to kind of keep it stationary. But if there is a net overall force, you get these different things happening. You get compression. So you've got two forces pushing towards each other, working in line. So one's going one way, one's going the other way along the same direction towards each other. Then you get compression. Compression is just basically squashing. Tension is almost the opposite. We have two forces working along the same line, but this time they're going away from each other. So that's like two people pulling on a rope. That's called tension. Tension is stretching. And bending, well, it's kind of what it says it is. When you have multiple forces acting on something, some pushing, some pulling, some twisting, but instead of it just getting longer or shorter, in some senses, here on this side, that would be in tension, and this side would be in compression. So that's kind of like both of them happening at the same time on the object. So if you have a net force on an object, you either get acceleration, change in direction, or change of shape, which can be compression, tension, or bending. When we talk about changing shape, there are things that can happen when it changes shape. Some things you can change their shape for a little bit and then they go back. Sometimes you can change their shape and they don't go back. So if I have a piece of plastic, if I bend this and let go, it returns to its original shape. Bend and return. That would be said to be elastic. It's not made of elastic. It is elastic. If you stretch a material, where's my highlighter? If you stretch a material, and then when you stop stretching, when you let go, it goes back to its original shape. That material is said to be elastic. So, oh, that wasn't supposed to happen. Stretch, let go. It goes back to its original shape. That's elastic. I just broke that. Sorry. If you stretch a material and it doesn't go back to its original shape, not breaking like this, but like say you get a bit of blue tack and you pull it and then you let go, it doesn't reconvene, it doesn't come back together. That means the material is plastic or behaving in a plastic way. Elastic materials stretch, let go, and they go back. That's elastic. Stretch, let go, they don't go back. Then not elastic. Not elastic is plastic. Things can start off as elastic and then go plastic. So, for example, you can have a spring which you stretch a little bit and then let go and it's fine. But if you pull it too much, it will unwind and become plastic. Good things to note down. The difference between elastic and plastic. Pause, copy it down. Okay. And here we have some pictorial examples of elastic and plastic. So if you start off with this block here, it is a piece of metal and it is in tension because the two arrows are going away from each other along the same plane. So this object is in tension. And here we can see, well, it's not as easy to see. Let me explain. We've got two objects. If I pull it really hard like that, it gets a little bit thinner. But if I let go, it will go back to this state. Because all that's happened is I've pulled things apart and then I let go, it will go back to this state. But you can see here and further down, if you pull something too far, if you go too far, you start damaging it, the walls and things start breaking down. This is called necking because it gets really thin. If you pull it too much and let go, that kind of dent, that neck in the material is now there. So letting go won't make that disappear. So that is now plastically deformed. Here is a kind of more extreme version of what I was saying. You have a spring like this. And if you pull the spring in both directions and then let go, the spring normally goes back. But if you pull it too hard in both directions and let go, it won't go back. You've made an elastic thing behave plastically. Now, if we were in school, we would be doing an experiment, but we're not, so we can't. But you could if you wanted to. If you use this table and you click on that link up here, it will take you to PhET, which is the online physics simulation, which is amazing. And if it wasn't for PhET, well, I don't know where we'd be. But you can do this experiment online. But what we would do originally, you would have a spring like this, and you attach your spring to a clamp stand. And then before you do anything, you measure the original length of the spring. How long is that spring to start with? The ones at school are about 2.5 centimeters. You then put on a weight. It might tell you it in grams. It might give it to you in newtons. You put on a weight, and then you measure how much the spring has increased in length. That's called its extension. So if originally it was this length, 2 centimeters, and now with all these springs on, it's gone this long, 3 centimeters. Its extension is, for example, 1 centimeter. The extension is how much longer has the spring got. You can do that if you do this experiment, or we would do it at school. If you're doing it at school, you'd have to be careful. You might put on about a kilo on here, and if it snapped, one, the spring could fly from your face. Two, the weights would drop on your toe and break them. So it's slightly safer being at home, but probably less interesting. So if you'd like to have a go at that experiment, here's a good table. And what you would do is you would do 6 different weights: 1 Newton, 2 Newton, 3 Newtons, 4 Newtons, 5 Newtons, and 6 Newtons, and see what happens to the length of the spring, or more importantly, the extension of the spring each time. If you want to do that, copy down that table and have a go at the experiment. Unpause when you're done. But I know, because the last time I got you to do an experiment, so many of you lied and pretended. You made up your results and they were awful. Some of you, it was a joke. So I know that's not going to happen. But the important thing is the results. And here we have some results. And I'm going to ask you, though, to sketch down. If you did the experiment, maybe do a little graph of it. Do an Excel sheet, that's fine. But if you didn't, here is a really good example of a graph of what you should have seen. Sketch the graph. Sketch the graph, pause, sketch, and undo the pause when you're done. Okay, so if you did this correctly, and you have this graph, you have extension on the x-axis and force on the y-axis. Normally it'd be the other way around, but we'll see why in a minute. And if you plot this graph and you get a straight line, that means your spring is doing something called obeying Hooke's law. Hooke is the law. And Hooke's law basically says if you, what does it say? My brain's not working. Yes. The force is the extension is directly proportional to the force applied to the spring, which basically means if you put whatever you put on the spring, the extension, it will extend in a proportional manner. So for example, in this one, you put 1 Newton on the spring, it increases by 0.1 meter. 2 Newtons, it increases by 0.2 meters. 3.3 meters. So the extension is proportional to the force. They go up in equal steps. It's a nice straight line through the origin. It's directly proportional. Hooke's law says the extension is directly proportional to the force. And if it's a law, you normally get an equation with it. So F equals KX. And here it is. F is the force that you've put on the spring. K is something called the spring constant. And X is the extension. And the spring constant is just something, a number related to the spring. It tells you how springy or not springy a spring is. If you then use this graph to calculate the gradient, you can get the spring constant, because the gradient is, do this, yx. So y over x is the same as f over x, which is equal to k. So if you do this experiment, or you just copy the graph, and you get a nice straight line, we know that spring obeys Hooke's law. And you can use the graph, the gradient of the graph, to work out the spring constant. You could, because ours is a lovely straight line, just choose this value here and this value here, put them into the equation to work out the spring constant that way. But the better way is to do the gradient. So, Hooke's law. The force exerted by a spring is equal to the spring constant multiplied by the extension. If something obeys Hooke's law, the extension of the spring goes up in a nice equal steps compared to the equal steps of the force. It's directly proportional. Positive correlation, directly proportional. Hooke's law. So, time for some questions. Quite a few questions, but they're all quite small. In this, here's another example of the experiment that you might have done. Here we have a graph of force and extension again. Forces in newtons, no, extensions in centimeters. What would be the independent variable in this experiment? Independent. No, there's only two variables. One's extension, one's the force. Which one did you choose? If we were doing the experiment, which one did you choose? Independent variable. And which one is the dependent variable? Which one changed because of your actions? The independent and the dependent. And then, question 3. Can you just describe the relationship between force and extension as shown by the graph? Does that graph obey Hooke's law? Same graph. Can you use the formula, spring constant is force divided by extension, to calculate the spring constant of the spring? Pick a point, somewhere on the wire, on the line, work it out. Then, can you work out the gradient? Let's see if we can get a nice line for you. That's a really bad line, sorry. There we go. Work out the gradient. Compare the two. A spring is an elastic object, as long as you don't overstretch it. It means that you deform it, change its shape, it goes back to the original shape when you let go. So a spring is an example of an elastic object. Can you think of another object that is elastic, or another material that has elastic properties? Dough or potter's clay are plastic materials. Describe the difference between plastic and elastic behavior. Basically, if you stretch them and let go, what happens? Explain why each of the applications below uses an elastic or plastic. So 8, 9, and 10, the first thing you do is either say elastic, plastic, and then say why. Moving parts on a trampoline, they're made of elastic. Why? Why is it important? Elastic materials used in tight-fitting sports clothes. Why is it important that they are elastic? Clay is plastic, which is used to make pots and sculptures. Why is it important that it's not elastic but plastic? Number 11, a spring has a spring constant of 2 newtons per centimetre. Spring B has a spring constant of 20 newtons per centimetre. Which spring is stiffer, as in harder, to extend? Can you explain your answer? Which? Think about it. Which requires more force to change the distance? Change its extension. Which requires more force to change the extension? 12. A spring has a spring constant of 3 newtons per centimetre. Calculate the force needed to extend it by 8 centimetres. Write the unit in your answer. Remember, F equals kx. Okay? A student exerts 2 newtons of force on a spring with a spring constant of 10 newtons per metre. Calculate the extension of the spring. Remember, F equals kx. That's not an x. That's an x. A spring whose original length is 7 millimeters lengthens to 10 millimeters. What's the extension? When a force of 0.4 newtons pulls on it, calculate the spring constant. So that one you have to work out the extension first. A particular type of spring has an extension of 6 centimeters when hung with a mass of 100 grams. A mass of 100 grams is hung from 2 of these springs in parallel, side by side. Suggest whether this extension would be more or less for one spring. And can you predict what the value of the extension would be? So that's saying finding 2 things that are similar. So instead of just having one spring, you have 2 springs exactly the same side by side, and then you hang the same thing off both springs so that whatever it is hooked on both springs at the same time. So they're side by side. What will be the effect? Now, for 16, it says the same 100-gram mass is hung from the 2 springs in series. So whereas before they were like this, so they were fixed at the top, and then you hook on both of them. Now it says these springs are in series, end to end, making a really long spring. So one spring is attached at the top, and then you hang the 100 grams on the bottom. Okay? Suggest whether the extension will be more or less for one spring. Can you predict what the extension might be? And what are the property of a spring that allows Newton meters? You remember what a Newton meter is? It's the thing with the hook and spring, and you lift like your pencil case up and your bags up in year 7 to determine what the weight of things are. What is it, the property of springs that allows Newton meters to have a linear, uniform force? Good. Sure you can. That's it. Good luck answering the questions. There's quite a few, but they're all quite simple. I know you can do it. If you have any questions, just ask your teacher. Don't forget to label your questions clearly when you're writing the answers. It makes it easier for us to check. Okay, love you. Bye.